All right, so we've made a secondary cation. And again, you know you have to go through a cation because the molecule rearranges. You should think it's going to be a cation. You got no good nucleophile or strong base. And that's going to suggest that you go SN1 or E1. And both SN1 and E1 go via a cation. So once you get to this secondary cation, look at your stability. Secondary cations are less stable than tertiary cations. And the other part of that is, remember that so the trigonal planar carbocation, the formally positive carbon, is going to be sp2 hybridized. It's got this vacant p orbital. Electrons around it are stabilizing that. So on the beta carbon, so this is the alpha carbon. On the beta carbon, any group attached to that beta carbon, the sigma electrons are going to be stabilizing that p orbital, right? If that R is an H, that's how you get the E1 reaction. A weak base can come take that H and make a pi bond. But the other thing that lets happen is, if the beta carbon would end up being a better carbocation, this R can just move over there, right? It's interacting. The R with its electrons is interacting with that carbon. So if the molecule would be more stable by that R group moving over, that will happen. And so what happens in this case, and let me just draw in, one of these methyls is going to move. And you know, I mean, the other thing is, you can just look at what has to happen in this reaction. You know that one of these methyls has to move to that carbon. Right? The way this works out, this methyl takes these two electrons and moves there. It's called an alkyl or a hydride shift, a rearrangement. And it's actually covered in chapter 6. For some unknown reason. Carbocations are covered in chapter 6. So that methyl takes two electrons and moves to the carbocation. And then what you get this. I'm just drawing that blue one in so you can keep track of it. Yeah.
So that rearrangement just happens to make it more stable.
Exactly.
Before it attacks the
Yeah. So this, you know, the methyl and its electrons are interacting with that p orbital. And that's a bonding interaction. And so if the methyl being bonded to this carbon is more stable than being bonded to this carbon, it will move. And the way you keep tabs on that, basically, if you make a carbocation that could become more stable by rearranging, that's going to happen. Like if you need to predict it. All right? So a secondary carbocation is a lot less stable than a tertiary carbocation. If this, sorry?
I didn't mean to interrupt you. Sorry.
No, it's fine.
Can that occur anywhere on the molecule as long as any spot is more stable, or does it need to be within a certain bonding?
It's got to be, that's a good question, right? If you had like over here, it really needs to be next to it, right? It's going to be a group on the beta, any group on the beta carbon can move, right? So our initial alpha carbon has two different beta carbons. There's 3 protons on this beta carbon. There's two methyls and a propyl on this one. So honestly, the propyl could move as well. Right? Any of those 6 things, the 3 protons here, the 3 groups on that beta carbon can move. H moves a little easier than the alkyl groups, and a smaller alkyl group moves a little easier than the bigger groups, but not by a lot. All right, so the H's don't move because if you moved one of those H's to the carbocation, you'd get a primary cation. That's the wrong direction. That makes the cation less stable. Okay, so in this case, either of these methyls moves, you get a tertiary carbocation, you get the chemistry you expect here, and now to get to that final product, the chloride attacks, and there you go. That's, so like I said, it's a long mechanism. And because that chloride is attacking a planar atom, a planar carbon, it can come from the top, it can come from the bottom, it can come from the front, the back. It's 50-50, right? I can hit from this side, I can hit from the back side. And so this is going to be racemic. This carbon will be, half of it. I've drawn it, and this is how we draw racemic chiral centers. You don't show wedges and dashes, you just show them all as lines. Clearly, all four of those bonds are not in the same plane. Half the molecules will have a dashed methyl, half will have a wedged methyl. Half will have a dashed chlorine, half will have a wedged chlorine. If you show chemistry there, if you show stereochemistry there, if you write a wedge and a dash there, you've got to write racemic, or you've got to write the enantiomer something. So this is 0% E. So take homes there. Sorry, go ahead, Max.
So with the other cases where OH was a leaving group, there was like inversion and retention.
Yeah.
Like in this case where you're protonating it, will it always end up being racemic? Or is
Yeah.
Okay.
So yeah, you've got a way to turn an OH into a leaving group that inverts the chemistry on the carbon with the OH. You've got a way to do it that retains the stereochemistry with the OH, and then you've got a way to racemize. Yeah.
So what happens if you're not doing E1 or SN1 when you have to do like inversion of stereochemistry? What would be the percent E for something like that?
So and there was something else I was going to come back and do. I can't remember. So really, if I ask this, so the only two I don't want to teach you how to take my tests. That's not your goal here is not to learn how to take Paul Jones's test, because there's not much money in that for you after this. Once you get out of this class, that skill will not serve you in any way. But really, the only two numbers, precise numbers I could ask you for, would be 0 and 98. Right? So if it's an SN1, or if it goes through a carbocation, it's going to racemize, and you'll get 0% E. What's that?
Racemize is a cool word.
It is. It'd be a good IMT name. The other number is, if it's SN2 and every chiral center inverts, 98, you get the same number. Like, those are the only two exact numbers that would make any sense. And so I haven't wanted to get in, I think we got into this in the offside. Like, sometimes a secondary carbon, if you have a leaving group on a secondary carbon, you might do a reaction that's mostly SN2, but some of the molecules would be SN1, right? SN2 is slow on a secondary carbon. SN1, if you put it in the right solvent, might be a little faster than, so you might see like some SN2 and some SN1. And if that happened, if there was some SN2 and some SN1, your EE wouldn't be 0, because it wouldn't all racemize. But it wouldn't be 98 either, because, so what would happen is every molecule that undergoes SN2 would invert. Every molecule that undergoes SN1 would racemize. So half the SN1 molecules would end up with an inversion, and half would end up with a retention. And what you'd find then is the EE would be somewhere between 0 and 98. I mean, between 0 and 98 is a wide number. And so I could give you that and say, if I'd asked that, if this was such a reaction, it's not. This reaction goes through a cation, you get complete racemization, 0% EE would be the answer. But if the answer I was looking for here involved some SN2 and some SN1, you couldn't give me a number. But you could tell me it's going to be lower than 98. Like, it won't be 0, it won't be 98, it'll be somewhere between. That's the best you can do. All right, so there was one. What did you guys ask? You asked for a methyl. I know what it was. Okay.
We're going to ask really quick.
Yeah.
If you have, so in a problem where you have an OH group, right, like this,
Yeah.
and you don't see either of the first two options where you see that specific product that you need,
Yeah.
you can assume it's the third option, right?
If you need it to move, yeah. So the other thing is, and I can't remember if it's on there or not, like if you have an alcohol and a strong base or a good nucleophile, like it might just not react. Like OH, like it doesn't have to react. So hydroxide's not a leaving group. So the only way, where are my three options? I got rid of my three options. No, I didn't. You're over here. Yeah. All right, so your options are thionyl chloride to turn the OH into a chloride.
Wait, no, that's.
Huh?
Yeah.
You can use tosyl chloride and a base to turn the OH into a tosylate, or you can protonate the OH. But protonating the OH requires a strong acid. So you can't just protonate it because you need it to be protonated. And it's not just like introduction to organic chemistry students doing this. We do it all the time in the lab. Like I need this to happen, so open a prayer. I'll pour these chemicals together and help something happen. It never works out. Right? So if I need to protonate an OH, I can't just like hope that happens. I have to put a strong acid in to do that. And that can be a really bad idea. Like mixing things with strong acids is a bad idea. Like this is a very simple molecule. The only functional group is an alcohol. If there's a whole bunch of other functional groups here that might be acid sensitive, it's chemistry you guys don't know yet. There are functional groups that you can't treat with strong acids because they fall apart. So then you would have to turn this into a chloride or a tosylate. All right, so you guys asked what would happen if there was a methyl. I think this is what you were. Well, it won't matter at that point. So now we don't have any chiral. So if we treat this with HCl, let's do the first two steps. Right, so if you protonate the OH, water leaves. Now you have a tertiary carbocation.
So you don't have to rearrange.
So it might rearrange. Like now if it rearranges, the two cations are kind of equally stable. And so it might rearrange, but it wouldn't completely rearrange.
So how do we indicate that?
Like if I asked you for the product, I would just draw that as a straight S and 1. Well, again, it depends on the temperature. Right, if I said 100 degrees, then this is going to be E1. Sorry, water. Whatever, water or... Right. 100 degrees there would tell you elimination. So really, the temperature should only come in once you've sort of got to E1 versus SN1 or E2 versus SN2. E versus S, you look at the temperature, higher temperature favors elimination. But if this was a lower temperature, and this would be racemic. Well, of course it's going to be racemic. We didn't ever have any stereochemistry there. If you did say it rearranged, I'd probably be okay with that, right? So rearrangement to a tertiary carbocation, that's okay. Like it's always okay. And you asked earlier, like if there was a group way over here. So you can't migrate there directly. I don't know how much to get into this with you, like, but you could have secondary rearranged to secondary. So like hydrogens could hop down the chain and eventually make the tertiary. That takes time. Like if you treat the reaction harshly enough, so high enough temperature, strong enough acid, you might eventually get this. But it's not as likely. You guys really should limit yourselves to 1-2 rearrangement.
So it could be almost like resonance, not in the sense that, not like the mechanism, but in the sense that it can hop.
Yeah. And we actually talk about this being kind of resonance-like. I hesitate to draw this. Where's mine? I think I So I drew this earlier, right? So when I say that there's this interaction here, if the two carbons are actually equally stable, so sort of this tertiary to tertiary, then the way that structure actually looks that H is halfway in between. It's bonded to both carbons. Doesn't have a full bond to both carbons. It's called a 3 center 2 electron bond. So you've got 3 atoms basically sharing the 2 electrons, and that's kind of like it's a phenomenon similar to resonance. Called it hyperconjugation. I'm not going to get into it. That you're not going to need to know what that was in the exam, but you should always be aware that if you make a carbocation, anytime you make a carbocation, so if I'm asking you to predict a product and you think it would go through a carbocation, you should look and consider, will it rearrange? Like especially if you make a secondary cation. If you make a secondary carbocation and it can rearrange the tertiary or a resonance stabilized one, it's going to do that. If I ask you for a mechanism to explain like how, a product where the carbons, where our groups move, a group comes off carbon 2, goes on carbon 3, you should consider a rearrangement. Questions about that?
So I'm a little confused on the first step of the mechanism, because I just drew like water coming off initially as opposed to the initial step where the H comes on. And
How'd you get water there?
Well, the H has to come there.
Yeah, so you've got to do this step to get water on.
Yeah. Okay, yeah, that just corresponds to the protonation step, right?
Right, yeah. So if you like water's gonna leave, but if you did that, if this was like problem number 2, draw a mechanism for this reaction. If you start here and then draw everything else fine, you're not gonna get full marks, but you're not gonna lose.
Yeah.
Right? Like I would kind of do every step is 20% or so. What is this? 1, 2, 3, 4 steps. So every step is 25%. Yeah, mechanisms get lots of partial credit, especially in Orgo 1, where like this will be the first exam where you guys have to draw a mechanism. And I mean, I can't say it any plainer than that, right? You're going to have to draw a mechanism on this exam. So the mechanism, the acid-base mechanism, SN1, SN2, E1, E2, and this rearrangement. It's going to be one or some combination of all those.
Is this one just like way harder than the other ones?
This is about as hard a one as you could get, right? You're protonating an alcohol, so and if you think about the basic step, chapter 6 breaks mechanisms down into fundamental steps. So you got a proton transfer step, you got a leaving group leaving, cation rearrangement, nucleophilic attack, and that's it, right? So if you look at chapter 6, it sort of breaks them all down into types of reactions. If you need to. It's 12:50, the clock's wrong, so if anybody needs to take off, they can. I can stay a couple more minutes if you have questions. Or we can be done. I'm fine with being done too, if you got questions. Yeah.
So, kind of dumb, but are there any other like leaving group looking groups like VOH that aren't technically leaving groups that need to go through a similar procedure?
There actually are a lot more leaving groups than sophomore organic chemistry text lets on. Leaving groups I'm not going to ask you, right? The leaving groups I want you to know are iodide, bromide, chloride, sulfonate ions, and then neutral things like water or an alcohol. So if this wasn't OH, if say that was O-ethyl, and you protonate it, O-ethyl can leave. Or sorry, ethanol can leave. Anything that's a weak base can be a good leaving group. And so there are other ones, especially biologically. So when you guys get to biochem, and I don't know, it also depends a lot on who you take biochemistry from. All right, so biochemistry is cross-listed between biology and chemistry, being sort of part of both. if I had my way, you guys would all take biochem from the biologist and from the chemist. Because the biologist sort of stands on an organism and look down at a cell, and chemists sort of stand on an atom and look up at a cell, right? And so really, to understand biochemistry, you need both perspectives. They don't let us require that much of you. So, and my advice to you would be, if you're a biology major, if you like if that's where your strength lies and your interest, take biochem from the biochemist, or take biochem from the biologist. If you're a chemist, if you liked organic chemistry more than you liked, I don't know, Bio 150, take biochem from the chemist. I suspect when you get to any kind of professional school that requires biochemistry, like med school, whatever, you'll sort of see it from the biological perspective, right? Like a doctor is more of a biologist than a chemist. I don't know where I was going with this. In biochemistry, there are a lot of leaving groups that are water soluble, have phosphates in them. So what you need to consider is, to be a good leaving group, a group needs to be a weak base when it comes off. So if you have it leave, the thing that leaves needs to be a really weak base. You're not ever going to see a strong base leave. Yeah.
You said that the mechanism could be broken down into 4 steps: proton transfer, leaving, carbon cation. What did you say the last one was?
Nucleophilic attack. Right, so this sort of, and this is just a Lewis acid base, chlorides being an electron donor. So the nucleophile can attack, so an SN2 is a nucleophilic attack with a leaving group leaving at the same time. So it's 2 fundamental groups of arrows. And that's not a bad way to do it. And I was saying to someone this morning on office hours, like, there is quite a bit of memorization in this class. But you should be trying to memorize all of it. Memorize some toe holds so that you can jump off there. And like I said, you're going to, like, water is a weak base. So then that means any molecule with a neutral oxygen that's got 2 covalent bonds, that's going to be a weak base. You don't have to memorize every weak base. But if the oxygen in a molecule looks like the oxygen in water, it's a weak base. If hydroxide is a strong base, so if there's an O with an anion in 1 bond, that's going to look like hydroxide. That's going to be a strong base. Yeah.
Has anyone tried the mass spec worksheet, just out of curiosity, because I've been working on it for like 3 days and I cannot.
The mass spec for this class?
Yeah. I don't know. You
This
did?
this class.
Yes. Not for lab, the worksheet you put on campus.
So it's not just mass spec though, right? It's
Mass spec IR.
okay, good. No, I was concerned I'd given you the wrong sheet up.
It was sorry. I just wanted to know.
No. It's a good, like, if you've been working at it 3 days, you should probably try to nail down some specific questions to email me. Like, I don't have office hours this afternoon, but if you email me, The other thing I'll say about that sheet is, one of the problems on there is, here's a whole bunch of spectra, put a structure together. That question won't, that kind of question will not appear on exam 2.
That's the one that I think.
Are the other questions make sense?
Yeah, it makes sense, and I think I really get it. It's just like I've been sitting at this like kind of.
Well, let's talk about it, because that question will be either on exam 3 or it's definitely on your final project. So we need to discuss it, but you're not in imminent danger from seeing a question like that on exam 2.
Which question is it?
The one where it's just a set of spectra and you have to produce a structure that goes along with it.
And so those will be graded the same way the acid-base homework is graded?
Yeah, and maybe not even, I'm going to be, like, I had time on the acid base. There's going to be a time crunch on these 2 worksheets. So it may be that I just scribble a couple of corrections and give you guys a grade. So, and even the acid base, I didn't grade that nearly as harshly. I think I took some people by surprise that they weren't just 15s. But, like, I didn't take a lot of points. If you missed everything, I think you got a 12 or something. So it's kind of like 3 categories of grades. These, because I want to get them back to you, I'll probably do it faster, and the keys will go up. So.
Thank you.
You bet. You guys have a good